There is a carbon atom in your right thumb. Right now, 6 protons, 6 neutrons, 6 electrons in their probability clouds. That atom is about 4.5 billion years older than you are. It was forged inside a star that died before the sun was born. After you die, it will leave your thumb and become something else. The funeral industry would prefer you not think about this too clearly. I want to tell you why. That atom might end up as a leaf on a tree, or a molecule inside a fish off the coast of Norway. Or, 3 centuries from now, the right thumb of a child not yet born. Look at your hand. Just look at it for a moment. I want you to understand what is inside it. The calcium in the bones of your fingers, every calcium atom, every single one, was manufactured inside a star, not in metaphor. In fact, the iron in your blood, the iron in the hemoglobin pulsing through your wrist right now, was made in stellar furnaces. The carbon in every protein, every fat, every strand of your DNA, carbon comes from one specific reaction that happens only inside the cores of red giant stars at temperatures around 100 million degrees. The oxygen in the water that makes up about 60% of your body, same story, slightly different stellar furnace. The phosphorus holding your DNA together. The sodium and potassium that your nerves use to fire signals. The zinc in your immune cells. The iodine in your thyroid, the cobalt in your B12, the molybdenum in some of your enzymes. Every one of them, made in stars. There is no factory on Earth that makes the heavy ones. There has never been. They are all imports. So how did they get made? In 1939, a German-born physicist named Hans Bethe, who had emigrated to the United States and was teaching at Cornell, published a paper in the Physical Review called Energy Production in Stars. Bethe worked out, on paper by hand, the nuclear reactions by which a star like the Sun produces its heat. The mechanism is this. 4 hydrogen nuclei, just 4 protons, fuse together through a chain of intermediate steps to form one helium nucleus. 2 of the protons convert into neutrons along the way, releasing positrons and neutrinos as they go. The mass of the resulting helium nucleus is slightly less than the mass of the 4 hydrogens that went into it, about 0.7% less. That missing mass becomes energy, by the famous equation E equals mc squared. And that energy is what makes the sun shine. The sun has been doing this for 4.5 billion years and has used up about half of its hydrogen fuel. It has about 5 billion years left. Bethe won the Nobel Prize for that work in 1967. He also worked out a second reaction, the carbon-nitrogen-oxygen cycle, which is the dominant energy source in stars, more massive than the sun. But hydrogen burning is just the first step. To make everything heavier than helium, you need something else. In 1957, 4 physicists, Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, published a paper in Reviews of Modern Physics that ran to over 100 pages. The paper is so famous it has its own nickname. It is called B²FH, after the 4 initials. And in it, they worked out, in detail, how every element in the universe heavier than helium gets manufactured inside stars. The trick in a star that has burned through its hydrogen is helium fusion. Helium-4 nuclei begin to fuse, and you get carbon-12. But there is a problem. 2 helium-4s combined make beryllium-8, which is unstable. It comes apart in a fraction of a second. To make carbon, you need 3 helium nuclei to come together at almost the same instant. The probability of that is, ordinarily, vanishingly small. Fred Hoyle, in 1953, made a prediction. He reasoned that since carbon obviously does exist in the universe in enormous abundance, and since carbon is necessary for any biology, and biology demonstrably exists, because here we are, there must be a quirk in the nuclear physics that makes the reaction proceed much faster than naive calculations suggest. He predicted that carbon-12 must have a specific excited state, a particular energy level, at right around 7.65 million electron volts, which would make the 3-alpha reaction resonant, and therefore enormously more probable. Then he went to William Fowler at Caltech, who ran a nuclear physics laboratory, and asked him to look for it. Fowler thought it was a stretch. He looked anyway. The state was there, exactly where Hoyle said it would be. That is a beautiful piece of reasoning, predicting a fact of nuclear physics from the observation that we and the trees exist. Hold that idea in mind, by the way. The universe contains carbon because of a quirk in a nuclear energy level. We exist because of a resonance. I will come back to this when we get to what the funeral industry sells you as a substitute for understanding it. Once carbon exists, it fuses into oxygen, oxygen into silicon, silicon into iron. And once the star has an iron core, the game ends. Because iron is the most tightly bound nucleus, and fusing iron costs energy instead of releasing it. The star collapses. Then it explodes. In that explosion, a supernova, the temperature gets so high and the neutron flux gets so intense that all the heavier elements form in seconds. Gold, silver, uranium, the trace metals in your body, all of it made in the last few seconds of a dying star, blown outward into space at a few percent of the speed of light, drifting through the galaxy for tens of millions of years, eventually mixing into the cloud of gas that collapsed and formed our solar system. Fowler won the Nobel Prize for this in 1983. Hoyle, who deserved it equally, did not get it, for reasons the Nobel Committee has never satisfactorily explained. Now look at your hand again. Every iron atom in your blood went through a supernova. Your body is, in a strict physical sense, a collection of stellar debris that has temporarily organized itself into a person listening to a lecture. That accounts for the origin. But knowing where the atoms were made does not tell you how they got into your particular body. So let me describe that next. The atoms in stars get redistributed into gas clouds. The gas clouds collapse and form new stars and planets. The planet cools, the water condenses, the chemistry of carbon begins. Plants eventually pull carbon dioxide out of the atmosphere by photosynthesis, splitting water molecules in the chloroplast, releasing oxygen as waste, locking the carbon into glucose. You eat the plant, or you eat the cow or the fish that ate the plant. The glucose travels through your digestive tract, gets cleaved by enzymes in your small intestine, the sugar molecules enter your bloodstream, and the carbon backbone gets incorporated into your fat cells, your muscle fibers, the membranes of your liver, the lipids of your brain. It is not a permanent incorporation. In the 1940s, a Hungarian chemist named George de Hevesy did some of the first experiments measuring how fast this turnover happens. De Hevesy is a remarkable figure in the history of science. He invented the technique of using radioactive isotopes as biological tracers, atoms of phosphorus or sodium or iron that had been made slightly radioactive in a reactor or a cyclotron, and he fed these tracers to animals, and sometimes to himself, and then measured the radioactivity in the various tissues over time. By watching where the hot atoms went and how fast they came back out, he could calculate the rate of incorporation and the rate of replacement for any element he could trace. He won the Nobel Prize in 1943. What de Hevesy showed, and what many investigators have refined in the decades since, is that the human body is not a static object. It is a flowing object. The atoms in your fat cells get replaced over months to years. The atoms in your liver, faster than that. The atoms in the lining of your intestine, the cells facing the food you eat, those get replaced every 3 to 5 days. Your blood, every red blood cell, is replaced about every 120 days. The myelin sheaths around your nerve cells turn over more slowly. Your skeleton holds on longest. The calcium in your bones turns over by something like 10% per year. After about 10 years, a healthy adult skeleton has been substantially rebuilt from new atoms. So consider this. The atoms that made up your body when you were 30 are not, in any large fraction, the atoms in your body now. They have left, they went out in breath, in sweat, in urine, in shed skin, in lost hair. They went back into the soil and the water and the atmosphere. They are out there somewhere, in plants, in animals, in clouds, in the bodies of other people. You are not a thing. You are a process. Now, if that is true while you are alive, and it is, the radio tracer data is unambiguous, then what happens at the moment of death is not, in physical terms, the beginning of some new kind of event. It is the continuation of a process that has been running the whole time. The metabolism stops. The pattern that was holding the flow of atoms in place stops being actively maintained. But the atoms themselves continue to do what atoms always do, which is participate in chemistry. Take cremation, because that is the cleanest case to follow. The human body is about 60% water by mass. The remaining 40% is mostly carbon, with oxygen and hydrogen bound up in the organic molecules, nitrogen in the proteins, calcium and phosphorus in the bones, and a long list of trace elements in smaller amounts. When that body is placed in a cremation chamber at temperatures around 1,600 degrees Fahrenheit, the water boils off first, in the first few minutes. Then the organic molecules combust. The carbon in those molecules binds with oxygen from the air to form carbon dioxide, which rises up the chimney and into the atmosphere. The hydrogen, also bound to the oxygen, forms water vapor, also up the chimney. The nitrogen in the proteins forms various oxides of nitrogen, also up. What is left behind in the chamber is the inorganic skeleton, mostly calcium phosphate, which is the mineral phase of bone. That is what the family collects from the crematorium in an urn. Calcium phosphate, ground to a uniform white-gray powder, about 4 to 6 pounds of it, in a typical adult. Not soft, fluffy ashes the way the word implies. Pulverized bone. A typical adult body contains about 16 kilograms of carbon, roughly 35 pounds. When combusted, that carbon binds with oxygen to form about 59 kilograms of carbon dioxide. That carbon dioxide rises into the atmosphere, where it joins a vast and active reservoir. The average residence time of a particular carbon dioxide molecule in the atmosphere before being absorbed somewhere is about 4 years. Some of it dissolves into the surface ocean. Some of it gets pulled into a plant by photosynthesis, the chloroplast splitting it apart and locking the carbon into glucose, exactly the same way the plant once locked the carbon that was eventually in the body. A leaf on a tree 200 miles downwind 2 months later may contain atoms that were, a year ago, in a person's lungs. Burial works the same way at a slower pace. Bacteria do most of the work in the first months. They break down the soft tissues. They release the carbon and the nitrogen back to the soil and the atmosphere. They participate in a complex chemistry that ecologists have studied in detail. Insects participate. Fungi participate. The calcium phosphate of the bones lasts longer, decades to centuries, depending on the soil chemistry, the moisture, the temperature. But it too eventually dissolves, and the calcium and phosphorus return to the soil, where plants take them up and incorporate them into new tissue. So the picture is this. Your body, during life, is constantly exchanging atoms with the environment. And after death, the exchange completes. There is no remainder. Every atom that was in you came from somewhere and goes back to somewhere. The universe runs a strict accounting. The atoms are conserved, which raises the only really interesting question. If your atoms are not yours, if they were borrowed during life and returned at death, then what exactly was you? I have spent some time on this question, and I think the answer is reasonably clear if you are willing to look at it directly. You are not your atoms. The atoms are interchangeable. A carbon atom that was in your liver in 1970 is possibly today in the muscle of a fish off the coast of Norway. And there is no physical sense, none whatsoever, in which that fish muscle carbon atom is any different from the carbon atom that replaced it in your liver. Carbon is carbon. 6 protons, 6 neutrons, 6 electrons. Quantum mechanics is very strict about this. Identical particles are exactly identical. There is no label, no serial number, no provenance written into the atom that says, this carbon used to be a poet, and that one used to be a mechanic. The atoms are completely fungible. So if the atoms are interchangeable, what holds you together as you? What is preserved? The answer is the pattern, the arrangement, the information, the way the 7 octillion atoms of your body are organized, connected, talking to each other through electrical signals along nerves, through chemical signals in the bloodstream, encoding memories in the connections between brain cells, encoding your face in the protein folds of your skin, encoding your voice in the geometry of your larynx, encoding your gait in the calibration of your cerebellum. That pattern is what you are. The atoms are the medium. The pattern is the message. This is not a metaphor. This is the physical truth, stated as exactly as I know how to state it. You are, in the most rigorous sense available to physics, a configuration of matter that persists over time by constantly exchanging the matter while preserving the configuration. A flame on a candle works the same way. The flame is the same flame from second to second, even though the atoms inside it, the burning hydrocarbon molecules and the heated nitrogen and oxygen of the air, are constantly being replaced. You are the flame. The food you eat is the candle, and when you die, the pattern dissolves. The flame goes out. The atoms go back into the world. Now there is one more piece I want to mention. The information that was the pattern while you were alive does not necessarily vanish completely. Some of it propagates into the memories of the people who knew you, into the words you wrote, the things you built, the children you had, the small habits and turns of phrase that you taught to other people who taught them to others. Some fraction of the pattern, in heavily attenuated form, persists in the world after the body is gone. Not all of it. Most of it goes, but not exactly zero. Let me pause here and tell you which of these things I am telling you with confidence and which are softer. The strongest claim is that the elements in your body were made in stars. This is one of the best supported facts in all of physical science. The spectroscopy of stars, the abundance patterns of elements measured in meteorites and on Earth, the laboratory cross-sections measured in particle accelerators, the computer models of supernova explosions, all of these independent lines of evidence agree. B squared FH in 1957 was the foundational work, and the field has only refined it since. I would rank this claim as solid as the existence of atoms themselves. The next claim, that the atoms in your body are constantly being replaced, is also well supported. The radio tracer studies by de Hevesy in the 1940s and many investigators in the decades since have measured turnover rates in tissue after tissue. The numbers I gave you, 3 to 5 days for intestinal lining, 120 days for red blood cells, 10% per year for the skeleton. These have been replicated in many laboratories with many techniques. Solid evidence. The claim that what survives at death of you is the pattern rather than the substance, that is partly physics and partly interpretation. The physical part, that you are a configuration of matter and not a fixed collection of atoms, that is solid. The conceptual extension, that we should therefore think of identity as information rather than as substance, is a reasonable view. It is the view I hold. But it is an interpretation, not a measurement. Other physicists, equally good physicists, might frame the matter somewhat differently. The claim that the information of a person partially persists in the world through influence on other people and through writings and offspring and artifacts, that is true in a weak sense and false in a strong sense. The weak sense is just trivially true. Of course, your children carry some of your patterns. Of course, your friends remember you. The strong sense, that anything like you continues to exist in any meaningful way after the metabolism stops, that is not physics. That is hopeful talk dressed in physical language, and I would not want to mislead you about which is which. So, 3 tiers: stellar origin and atomic recycling, strong, unimpeachable. Pattern as identity, reasonable interpretation. Information persistence after death, weak and partly wishful. Now here is what I find curious. The funeral industry in the United States, by the 1980s, was a business of about $6.5 billion a year. The average funeral in 1985 cost somewhere around $2,000. The cost of a sealed casket of bronze or copper, a concrete vault to encase the casket, embalming fluid pumped through the arteries of the deceased, a plot of land in perpetuity at a cemetery, all of this is sold on the premise that something is being preserved. That if you spend enough money, you can hold the body, or the memory, or some essence of the person in place. That decay can be slowed. That the corruption of the flesh can be postponed. That there is some kind of dignity in not recirculating. I am not unkind about this. People grieve. Ritual matters. The handling of a body matters to the survivors, and the survivors are who the funeral is actually for. None of what I am about to say is meant to scold anyone for honoring their dead. Consider, for a moment, the person who has just buried a spouse, who sat in the funeral home and was walked through the catalog of caskets, who was advised to select the model with the rubber gasket and the protective vault, because, the salesman said, it will keep your loved ones safe from the elements, who has not slept properly in 2 weeks, who is signing checks that will arrive at the credit card statement next month, who took the comfort that was offered, because comfort is real and grief is unbearable, and made a decision in 2 minutes that will cost as much as a small car. I am not blaming that person. That person is doing exactly what humans have done for as long as we have had humans. We honor the dead. We mark the moment. We perform rituals that say to ourselves and to each other, this person mattered. But the physics tells a different story than the brochure does. The atoms in the body are not preserved by any casket. Sealed bronze, sealed copper, sealed concrete, sealed lead. The bacteria inside the body do their work, regardless. The chemical breakdown happens on its own schedule. The vault slows the return of the calcium and the phosphorus to the soil by some decades. That is the most generous physical claim one can make for it. The carbon, the hydrogen, the nitrogen, the oxygen, those still escape, in gases, through any container. The recirculation happens. It cannot be stopped. There is no casket that beats chemistry. An alternative to recirculation is being sold that the universe does not actually offer. A direct cremation, with no embalming, no casket, no vault, costs around $500 in 1985 and returns the carbon to the atmosphere within minutes instead of decades. The atoms get back into the world faster. The pattern was already gone at the moment of death, in either case. What is being purchased, in either case, is comfort for the living. That is real. That is worth paying for if it brings comfort. But it should not be confused with preservation of the dead. The dead are not preserved by physics. The dead are recycled. There is no exception. There has never been an exception. So here is one way to put it. A pharmaceutical company sells you a chemical that mimics what your body would do anyway. A funeral industry sells you a delay that the chemistry overrules. In both cases, the body's version is the original. The industry's version is the markup. You have heard, all your life, the phrase, ashes to ashes, dust to dust. It is from the Book of Common Prayer, from the burial service, written in the 1600s. The people who composed those words did not have spectroscopes. They had not seen the carbon-nitrogen cycle inside stars. They had not measured the turnover of phosphorus in bone with radioactive tracers. They had never heard of a supernova, or a Hoyle resonance, or a chloroplast. And yet they knew. They knew that the body returns to the dust it came from, that the dust came from somewhere, that whatever you are made of is on loan, that the loan ends. The science has only filled in the details. Carbon to carbon dioxide to leaf. Iron to soil to root to stem to fruit. Calcium to seedling to bone. The cycle is real. The medieval clerics had it right. They just did not know how right. Now go back to that carbon atom in your right thumb, the one I asked you to think about at the beginning, forged in the heart of a star 4.5 billion years ago, currently on loan to you. Listen to your own breath for one moment. Every time you exhale, you are sending some of those atoms back into the world. You have been doing it your whole life. Death is not the moment your atoms leave. Death is the moment the pattern stops holding them together. The atoms do not end. You, the configuration of them, does. And the world goes on, reconfiguring. Tell me what you make of that.